Before starting this lecture, let's review a couple of things that we know about the linear regression model and the OLS estimators. So we have a linear regression model. We make the Gauss-Markov assumptions. The explanatory variable is exogenous. The variance of the error terms is constant, equal to sigma square. We can estimate the unknown parameters beta 1 and beta 2 using the OLS estimator, and the estimates are called B1 and B2. With the exogeneity assumption, we know that these are unbiased estimators. So we know the expected value of B1 and we know the expected value of B2. If we have the full Gauss-Markov so that the error terms are also homoscedastic, then we're actually able to derive a formula for the variance of B1 and B2. And unfortunately, it turned out that those variances depends on this unknown parameter sigma square, which was again the common variance of the error terms. Well, in another lecture, we learned how to estimate sigma square. So even though I don't know sigma square, I can estimate it. And the estimator was named S square. And it was simply RSS over n minus 2. So the idea now is to take this estimator of sigma square, put it into the formula for the variance of B1 and B2, and we will then get an estimate of the variance of B1 and B2. So that's why this lecture is called Estimating the Variance of the OLS Estimators. Setup is the linear regression model with random sampling. If I now take the formula for the variance of B1 and B2, go back and check it out, and I replace sigma square with S square, the estimate, then I get what's called the estimated variances of B1 and B2. So for B1 it looks like this, not so important. For B2, incredibly important. This is the estimated variance of B2. And to signal that this is actually not the true variance but the estimated variance, we put a little hat on top of VAR. So it's the estimated variance. Now this makes a world of difference because this can be calculated from the sample. I can calculate S squared from the sample, and I can calculate the denominator from the sample. So again, let's have a look at this in a simulation study. I simulated data with a beta 1 and beta 2. My sigma square is 0.25. Here are the OLS estimates of beta 1 and beta 2. And here is the variance of B2. And if you look at the formula, you see that it includes B4 squared, that is, includes this guy squared, which is unknown to us, and that's why we painted it red. So the idea is simply to find the estimated variance of B2. I'll call it EVAR. It's not that easy to make hats in Excel. So look at this formula. I can just copy this formula, put it here, Control C. And the thing I need to do is to just change this here from sigma 2, B4 squared, to S2. And S2 is in the cell I22. Well, we also have it in cell B21. Use whatever you want. But this is now the estimated variance of B2, and sort of the whole point here is I can paint this green. That's just calculated from stuff that we know, so it's green. And since S square is pretty close to sigma square, the estimated variance of B2 will be pretty close to the true variance of B2. This thing here that I calculated in my cell B15 is a very important number. Why? Well, because it gives us a measure of precision in our B2. It tells us how certain we can be of our estimate. So a B2 with a high variance is not worth that much. Very uncertain in that case. A B2 with a low variance, that's nice. Then that means that we can trust B2. Now it's actually common to look at the square root of these variances rather than the variances themselves. But first, let's conclude the following. If the Gauss-Markov assumption is satisfied, like in our simulation study, then these estimated variances are actually unbiased and consistent estimators of the true variances. So you can think about it like this. If I F9 this sheet here, then the cell in B15 will on average be equal to the cell in B14. If I do this, you can see here it's above, here it's below, above, and so on. And on average, they will be the same. The square root of the variances are called the standard errors. And the standard errors are among the most important numbers in regression analysis. So if I go back here, if I take the square root of my estimated variance in B2, SQRT of this guy, then I get the standard error of B2. The standard error of B2. To be complete, let's paint it green. It's known as well. And you can get this number much more easily than going through all these long computations that we have done where we have derived this number from our sample. For example, if you use linest in Excel, if you use linest in Excel and you also include additional statistics, so you put a 1 here in the last one, stats, then you actually get the standard errors in the second row. You get B2 and B1 in the first row. That's B2 and B1. And these are the standard errors. So this is the standard error of B2 and this is the standard error of B1. Think about them as measures of precision in these guys. This is my best guess. This is how certain / uncertain I am about this estimate, 2.06. You can see that our computation here is correct. We got the same number as Excel. In eViews, you get the standard errors in the second column. So this 0.032975, that's the standard error of B2. It's a measure of how well we were able to estimate B2. This is the standard error of B1. It measures the uncertainty of this estimate. So just as an example, you can clearly see that this estimate of the intercept is way more uncertain than the estimate of the slope. The standard error is much higher here than here. A low standard error is what we're looking for because that means nice precision. Gretel does something extremely similar. It puts the coefficients in the first column and the standard error in the second column. I think they probably will be the same, and they are. We'll get to the third and the fourth column a little bit later.